Well, just finished folding the laundry here in Baltimore, and so I'm ready to give my presentation. Yeah, I'm going to be talking about metal building purlin line strength, and the key word here is by computation, which is a little bit different. Usually we're maybe thinking like getting purlin line strength from tests or from like equations, calculations in the code, but this is mostly by computation. And this is a metal building roof, and it's just steel as far as the eye can see. It's really a beautiful sight. The challenge is that there are a lot of structural details that need to be considered. I've made like a short list here, like pretty interesting sections, like point symmetric, shear centers are off from where where the load is going in, like partial bracing, roof slope, insulation, all kinds of different things. And this problem of just calculating maybe like a 4-span or even a single span, the capacity of the purlin in this situation, either in gravity or uplift, has been studied for many years. There are recently, though, code-based pathways for these types of, like for the computational approaches that I'm going to talk about, both in S116 and also in the Eurocode. So like we've made quite a bit of progress, and the reason why we're making more progress these days is because we have access to structural analysis software that can handle these types of weird purlins. Like usually we have to deal with these kinds of systems in the fancy finite element programs, the commercial software that we're used to dealing with, like the STADs and SAPs, like they don't have the beam formulations to deal with purlins and things connected to purlins. But there's programs like Mastan2, the new version of Mastan2, and the program that I'm going to be talking about tonight. So we have a way of analyzing this stuff, and we have the direct strength method. We have lots of system tests and simulations, and we have like a pretty like strong focus on characterizing the connections along with the components. So we have all of this collected over 60 plus years, and so the computation workflow can be as follows. Yeah, you can model the purlin line with the bracing and the bridging and the load eccentricities and the roof slope, like something like this picture here. And you can calculate the purlin deformations, the forces, moments, shear, and torsion demands. If you can put this structural analysis together, you can calculate all that stuff. We also know from studying this problem for a while that the free flange, the compressed flange, like if it's or the free flange, and when it's compressed, it wants to like move all over the place. It wants to move because it's being held onto by this pretty thin web, and it has a tendency to move sideways, and also it has some shear flow collecting. Like if you calculate the shear stresses in this cross section, you find that that's contributing also to the movement of the free flange compression. And so like if we include that, and then we like compare the demands to the strength limit states, and then so we can essentially do a simulated test, or like the virtual testing that has been talked about in this conference. Like you can load the purlin line to where the first limit state is reached, and that's your available strength. And so if you look back in the literature, like even going back to the going back to the 80s, like with Teoman Pecos, like he wrote software with a student or a collaborator for this exact problem. Galambos, like Ted did like standing seam roof connected to joists, and he was doing second order analysis with springs. Like it all looks the same. I think the nice part now is that we have the ability to like we've progressed where we can really get that type of software in like the hands of in everyone's hands. So how am I doing that, or how are we doing that? Sorry, let me. We're doing that. I've done it recently with the open source package called StructuresKit. It didn't came out of an AISI project, creating an example problem by computation using the direct strength method, and it just grew into this a package where you can analyze a beam connected to stuff with loads and do a second order analysis. And also like codes and standards libraries where you can like go ahead and you can calculate at least some of the equations. I don't have all of them in here, but you can calculate a lot of the equations that are in AISI S100 in this open source software package. And you can like do other stuff like solve and get the internal forces and do stuff with the cross section, and it's all here. And so like so now we have the computational workflow, and we have like some tools to do it. Like you could also do this same thing with the new version of Mastan 2 if you could wrap it in with some limit states checks. And so this was where the task group and the AISI task group led me to, or led us to. And so now but we were always wondering how we should compare this to tests, and so let's practice. We can actually compare the computational approach that is proposed here to experiments, and I picked a series of 50 experiments that I'm intimately familiar with, just because I was involved with them with my PhD student back in the day, and so we have like everything that you would ever want to know about these experiments. Like we have all the measured cross-section properties, material properties. We even conducted rotational restraint tests, or F tests. Like we know all the spring stiffnesses. We even know like the location of the screws here, and yeah, so we can run these tests. And this is what happens when you pull down the purlin in an uplift situation. So this purlin is flipped upside down, but you're pulling it down and it fails right here. It wants to move sideways, and it's combining with weak axis or strong axis flexure. And yeah, so it wants to fail like right here or right here in the uplift condition. All right, and so we can run that, and then so we can run the analysis, and we can throw like a limit state equation. This is like, I'm calling it the kitchen sink interaction equation. We're checking, it ends up being a yield criterion, but like it's checking pretty much this location for bending about the x-axis, bending about the y-axis, torsion, and also like movement of that flange as it wants to go sideways. Like all of that stuff is combined. And you can run this simulation by so if you want to use StructuresKit, you just type using StructuresKit, and you're using it, and then you can put in all the properties of your test, and then you can run your test. This includes all the stuff that we've just talked about, and then you can get like the tested strength. This is in pascals, which is like a weird unit. This is about like 13 psf, and you can compute it, and then you can compare it to the test pressure. So I did that for the 50 experiments, and like overall I was getting like pretty close answers for 50 tests, so I was pretty happy about it. And they're like, really, I just took all the information from the experiments, and then from here like you can get all like this cool stuff. Like you can plot things like the torsion, like displacements, and you can get all this fun stuff. So like, actually I'll ask, does somebody what does somebody want me to plot right now? Like someone just typed something in the Slack window. Like what are people interested in seeing about this particular single span purlin line? Plot the twist. All right, let's plot the twist. So we just go down here. Sorry. And you can plot the twist, which is B. And you got the twist. Sorry, like this label is wrong, but like you get the idea. So you can do everything. You can get lots of fun stuff. And you can get the demand to capacity ratio, and you can see like it's failing at midspan. And so pretty much you've run a simulated test in about this takes about like 1 second to run. I can tell you it took a lot longer to run those experimental tests, or the physical tests. So that's it. Like conclusions are that like structural analysis of metal building purlin lines is challenging. The research investment has paid off, and purlin line strength can be computed. And also give like a little open source software pep talk, because open means open. Like it's open source is different than like writing your code and then like making it available to people. Like open source means like you like it's in a format like GitHub where like people can interact and propose things, and like it's very collaborative. And so I just encourage everyone to learn open source languages and to code more and to contribute to your favorite packages. There's a lot out there, and there could be a lot more. All right, that's pretty much it. So thanks a lot, everyone.